All right. Well, let's try to continue from here. So as I said, in SI model, there is a susceptible population and infected, right? And susceptible becomes infected with time. Well, the total number of people is conserved, and we can write a differential equation that connects, that tells us the evolution of the number of, for example, susceptible of infected people. And the number of infected people at moment of time t plus delta t is the number of people at time t plus as many people as get infected during time delta t. And that is proportional to the number of infected people, because the infection spreads by infected people, times the fraction of susceptible people. Well, the reason for that is because it's only when infection goes from infected to susceptible, we get a new infected person, right? And beta is infection or contact rate, or how many contacts happens per unit of time. And then we can get a differential equation from this by moving this on the left and dividing by delta t, okay? So this differential equation, together with this first equation, s plus I equal to n, we can solve now. Oh, and we also will need to have initial conditions. We'll introduce them in a second. So it is convenient to actually use fractions of the population instead of actual population numbers, because, well, you will see why. So we'll introduce notation little I, which is a fraction of infected people, and little s as a fraction of those that are susceptible. So I wrote two equations. They're sort of symmetric in the world, they're asymmetric in the sense that this equation controls the number of infected people, and it's growing with time. And this equation, well, can be written the same way with the same logic, controls the number of susceptible people, and the number is decreasing with time, right? And this is a constraint. Now it is s plus I equal to 1, because these are the fractions of the population. So putting this together, we'll, for example, take this s and plug it in here. We'll get differential equation. And there is an initial condition for this differential equation that at the time t naught, we have I naught infected people. So again, if this is entire population, so here we have s, those susceptible, and here we have infected, and at time t round equal to 0, this I is equal to I naught, okay? And infection will propagate. The interesting part of this differential equation, of course, is the fact that here on the right-hand side, we'll have this product, I times I, 1 minus I. Now, do you know how to solve this differential equation? Okay, I can see you, but I cannot hear you. So guys, can you solve this equation?
Yes.
Okay, how do you do that? How would you do that?
You separate the variables, you split the differential, and then you integrate both sides with respect to their,
Yep. So I recommend you to actually do that later at home. I'll just show you the solution, which will be a logistic function. Of course, you know, just we're not gonna solve it, but we'll analyze right now the solution. Well, first of all, kind of checking the common sense, right? If I naught is equal to 0, for example, then nothing is going to happen, right? There'll be no infection propagation. So we need to have some I naught. We need to have some number of infected people. The other important features of this model is that when time goes to infinity, beta, the infection rate, is greater than 0. And if time goes to infinity, this goes to 0. And eventually we get I naught divided by I naught. And so I from t goes to 1, right? So which really means that pretty much everybody get infected. And here, this is, well, this is actually not X, but I from. This is a fraction of people who are infected. And we start here, and then infection propagates with time, and eventually we get everybody infected in population. So there is no more susceptible people. So as we started this picture, SI, we ended up with everybody infected. Okay, so this is absolutely a trivial model. The only point of looking at this model was to sort of get introduction to the ideas, and also to sort of familiarize yourself with this S-shaped curve, logistic growth curve. In fact, we'll see this curve a lot in the following lectures. And it comes from this sort of dynamics where you have infection, and infection propagates on the contact. Okay, moving on. So the next sort of more advanced model is called SIS model. So the idea is the following. There are also S people and I people, susceptible and infected people. And susceptible people can get infected. But the good news are that the infected people can actually recover. And so there is also this sort of flow of infected people back to the pool of susceptible people. Now, this model will probably model some diseases where you cannot get immunity, which is like flu, right? The fact that you just had a flu doesn't mean you cannot have it in the next week again. And so here again, the person recovers, but can again get sick. So there were the same constraints. There were only two types of people, susceptible and infected. But the dynamics is a little different. So if we look at, for example, the number of infected people as a function of time, the differential equation, and we can write it the same way as we did the very first equation, what it says is the following, that on one hand we have, so dI dt, first of all, the number of infected people is growing due to like the infection rate, right? The infection rate on the contact. But at the same time, the number of those people decreasing because of the recovery. And important here to notice the difference. Here it's S times I. So the infection rate is proportional to both the fraction of infected people, because you need to get infection from them, and the fraction of susceptible people, because the infection should go to someone. The recovery rate is only proportional to the number of infected people. Now, the reason this is important is because of the following. If at the beginning of the process there are a lot of susceptible people, this process can go pretty fast. But then it can slow down when the number of susceptible people gets smaller. And so what's happening is when the process starts, let's say right here, susceptible people, infected people, then this partition moves and you get, say, more susceptible, or some more susceptible, more infected people. But based on the sort of ratio of beta and gamma on the recovery and infection rate, we will get some sort of equilibrium situation. And you can have actually, depending on the ratio on beta to gamma, two types of equilibrium situation. One type is when you have some number of susceptible people and some number of infected people, and that balance will be preserved during the time. The other possibility is actually that disease will just go away and the susceptible people will dominate. And we'll see right now when each of those scenarios happens. Okay, so what we do here is we move from this equation, we'll take this equation, dIdt equation, right? We'll again substitute S from the S plus I equal to 1, and we'll get differential equation. So it's slightly different from what we had before. Instead of just beta, it has beta minus gamma. All right, any questions so far? So things obvious. Okay. So let's look at the solution. Well, we can get the solution. It's the same type of the solution as we had before, where what we just do is we just substitute for beta minus gamma. And there is a different, like a little bit different coefficient in front of it. But you can get it easily just by solving the equation. So what do we have here? Well, let's analyze. We're going to look at long times and see what happens with this equation. If beta greater than gamma, say here beta is greater than gamma, what we have is the following. So this is a positive number. There is minus in front of it, and time t. So when t is becoming very large, this becomes small, this goes to 0, and we get c over c, which cancels out, and then what's left is just this coefficient. And so this situation means the following, that when beta is greater than gamma, we'll eventually get some sort of equilibrium position where there is some number of susceptible people and there is some fraction of infected people. And we get this sort of balance. And the fraction of infected people is controlled by the ratio beta to gamma, right? And the larger beta is, the closer this fraction to 1. So again, beta is the rate of infection, gamma is the rate of recovery. So it's sort of obvious, you know, if infection is much faster, the rate of infection is much faster. If you get per unit time more people infected than recovered, eventually, the number of infected people will dominate. The situation is different when beta is less than gamma. When beta is less than gamma, you cannot analyze it that way. This number will not be small. It's actually will be, when time goes to infinity and beta less than gamma, this will be dominating term. Let's see if I can, yeah, I can erase. So when beta less than gamma, this is negative. Negative times minus is positive. Times large t, it's going to be a very large term. So it will be dominating. Everything else goes away. So this dominates. That's what's going to look like. But when beta is less than gamma, when time goes to infinity, this goes to 0. So pretty much I of t goes to 0, which means in this case, the infection will go away. And so that really tells you that the ratio beta to gamma is very important. It actually differentiates two types of behaviors of the system when time goes to infinity. So in fact, if we can, we can draw this solution, and we start with the same number of infected people originally, but depending on the beta to gamma, we get two different scenarios. One scenario is we get pretty much a stable situation with a lot of infected people, but it's also important to notice that, yes, it saturates, but it doesn't saturate to 1. There is still some gap in here. So, there is also, in case of beta less than gamma, infection will go away. One important point to sort of realize that in this scenario where you have susceptible and infected, and the stable situation where there is always some people who are not sick at the moment, we should realize that the people moving from this partition to that partition, and so the fact that there is a percentile of population that is not sick at the moment doesn't mean they never got sick. So this particular model assumes that pretty much anybody can get sick and later on recover, but there is a certain percentile of nodes or people that are not sick at any moment of time, right? And when time goes to infinity, it sort of stabilizes, and that's what it is equal to. Next time when we talk about networks, we'll look at this process as the dynamic of this process on the network. We'll see how some nodes can get infected, then recovered, then can get infected again, then recovered again. The point would be that when time goes to infinity, the ratio of infected nodes to recovered node will stay constant. All right, any questions about this model? Have you seen those models before?
Yes.
Yes, excellent. Okay, so then there is the last model that we're going to talk about is SIR model. And here the difference is the following, right? We have three compartments, S, I, and R. And in this scenario, people can get infected and then recovered or removed from the system. And the dynamics is also somewhat different. So the possible, I mean, eventually, what might happen is either everybody in the population or almost everybody will go through infected phase, and then we get pretty much everybody recovered or removed. So that's epidemic happened, or it could happen that the infection will just die out, and we'll still have some percentile of susceptible people and some percentile of recovered. And so these are the people who actually were sick, right? And that means in this scenario, there is a big part of the population that never got sick. And these two behaviors, they are also, of course, controlled by differential equations. So let's take a look at this differential equations. The idea is very, very simple and similar. So again, we start by looking at infected people. So the number of infected people is growing due to the infection rate. And it's proportional to the number of infected people and proportional to the number of susceptible people, because that's where the fresh people comes from. And at the same time, it's decreasing by the recovery process. Now, at the same time, there is this equation on susceptible people. Well, the number of susceptible people is just decreasing because they're getting sick. And the number of recovered people is increasing due to recovery. And obviously, there is the same gamma here, right? The recovery rate. And now, since we have three types of population, S, I, and R, well, they all add up to 1. So, you know, we can put together this system and try to solve it. Now, it's actually harder to solve this system than previous systems. And what we're going to do right now is we'll play a little trick. So first of all, we'll start with these two equations. We'll take this equation, and we'll take this equation. substitute infected into each other, and we'll get the following one. Now, this allows us to get rid of time in the equation and get the sort of phase equation or phase transition equation that that gives us connection between the number of susceptible people and number of recovered people. Now, this is, if you notice, in this equation, there is no time. Now, this is just a way to approach these equations. In fact, we will not be able to solve them completely. This is just a way to sort of simplify things. So, and then what we can do is we can go back, grab this equation, again, grab this equation, and plug our formula in, and we'll get this differential equation for R. Now, if we could solve it, we'll get R as a function of time, the number of recovered people as a function of time. You can write the solution of this equation. It's easy to write as an integral. Now, the problem is it's pretty difficult to take this integral, right? So analytically, you cannot do this. So we'll have to either numerically take this integral, or another option, just go back here, and here's your 3 differential equations, and just solve them. System of differential equations. So if we do this numerically, we can observe the following patterns, and that's sort of the essence of this SIR model and what made it very, very popular and important. So what's shown on this picture are 3 curves. Now, one curve is for susceptible people. So these are susceptible people. And if you notice, it starts with some number of susceptible people, and as time goes by, epidemic progresses, the number is decreasing. Now, the red curve is a number of infected people. And so what this model does, it shows you that initially we start with some number of infected people, then the number of infected people, the ratio of infected people grows significantly, and then it decreases with time. And it decreases, well, because you really don't get any more people to get infected. So there's this very sort of nonlinear behavior. And the blue curve is the recovered people. If you notice, it goes up, but it doesn't saturate to 1. So there is this little few people who actually never got infected, right? And so they're not recovered. But if we look at our diagram, the situation is the following. So we have susceptible initially, and we have some number of infected people, and then as time goes by, susceptible, infected, recovered. Then there is this moment where infected people, lots and lots, we're somewhere here. Then we get fewer of infected people and lots of recovered. And at the end, here is susceptible, and there is recovered. Okay, so what happened is we got an epidemic, and lots of people got sick. And if there's serious disease, well, lots of people died. And this is an epidemic, authorities would like to prevent. Now, this type of behavior happens when beta greater than gamma, which means that the infection rate is much higher than recovery rate. Well, in particular for this picture, it's just beta to gamma is equal to 4. The situation is very, very, very much different when beta is less than gamma. What happened in that situation is the following. Look at the infections. There were some infections at the beginning, and then they just die out. Well, infections, I mean. So if I show here susceptible and infected people, it's the volume, the ratio of infected people is not growing with time. It's just decreasing. It's getting smaller, and eventually we have a bunch of susceptible people and recovered people. So the total number of susceptible people, well, it dropped from the very beginning because some of them got sick, but it's still very high. And total number of recovered people is right here. So this is recovered, this is infected, these are susceptible. So if we compare those two pictures, they're entirely different, right? It's a very different world. Here we got epidemics. We got a moment when there are a lot of people are sick at the same time. In this model, we don't have it. And so probably this sort of predictive power of the model, that what made it so popular, that depending on the ratio, and sort of obvious ratio of beta to gamma, right, the rate of infections versus the rate of recovery, you can get so different behaviors. Okay. All right. So though we cannot solve this analytically, we can still look at some of the behaviors as time goes to infinity. And we usually like to do that because when time goes to infinity, and so in this picture it will be somewhere here, we would like to know, I mean, the result of epidemics is how many people actually recovered through that, or died through epidemics. And that's given by value of R at the very end. So we are interested to see this value or this value, right? And there is a dramatic difference in between them in these two different regimes. So it's very plausible that even doing some approximations, we should be able to differentiate between those regimes, between very large ratio of recovery and very small. So to do so, let's analyze this equation. What's obvious that it doesn't matter whether the behavior is like this or behavior was like that. When time goes to infinity, there is a saturation. And this saturation gives us idea how we can handle this the process. The fact that we have a saturation here really means that as time goes to infinity, the function doesn't change, and so derivative is equal to 0. All right. So derivative is equal to 0. We can take this and equate it to 0. Well, except for r now is not a variable. R is the value at infinity. Okay. So then we get the following equation. This equation is just what we had here. We equated it to 0. Now, another trick that we can play here, and again, this is, we're trying to do some estimate, right, is the following. At the beginning, at the very beginning, we had some infected people, right? And we had, we don't have recovered people, and we have susceptible people. And usually the number of infected people is much smaller at the beginning of epidemics than number of susceptible people. So S is much, much larger than I. And so then little s, which is a fraction, is pretty close to 1. Because pretty much everybody is susceptible. There are just a few infected people. And then we can write the equation the following way. We just get rid of S naught because it is close, very close to 1. Now, does any of you recognize the equation? Have we seen this equation before?
We saw this equation when we were talking about random growth models and the probability of the graph becoming connected or something like this.
Yes, absolutely right. So this is really the same equation as we looked at when we looked at random graphs, Erdős-Rényi model, and looked at phase transition, whether there is a gigantic connected component, if the people are connected, if all nodes are connected in the graph or not. This is exactly the same equation. And you know, if you think about it, we'll actually work more on this sort of parallel ideas later. But if you think about it, you know, the epidemic spread, if you think about networks, is when all the nodes gets connected into one big component, right? If all the nodes get connected, that's when epidemics can go through the entire graph. If they're not, it will not go. And so this is a connection, very, very clear connection between this and between random graphs and epidemics. And you're totally correct. This is the same equation. And so we solve it exactly the same way as we did with random graph model. So the idea is that this equation can have two solutions, right? One solution is at the point 0, where R infinity is equal to 0. And then, depending on the value of this parameter beta over gamma, it might have or might not have another solution. Well, here it says C because I copied it from other slides, but it's actually R naught. Okay, so how do we determine it? Well, we look at those two curves, well, at the diagonal line, right? And we look at the curve given by this equation. And in order for these guys to have non-zero solution, the second curve should actually be above the diagonal at origin, right? Then we'll have another solution. Yeah, and to do this, to find this point, yeah, we'll differentiate right-hand side, left-hand side, derivative here, and we differentiate with respect to R infinity, derivative, and take it at R infinity equal to 0. And if we just do this, what we get is R naught equal to 1, right? Where R naught is beta to gamma. So pretty much the phase transition, the control, the critical point is when beta equal to gamma. And we assume that's all along. This is just sort of a confirmation. So on the right-hand side here, we have a picture showing the possible solutions. So it shows the value of R infinity as a function of this R naught and beta to gamma. And what it says is when R naught is less than 1, so we are here, right? So beta less than gamma, which is infection rate is less than recovery rate, we're always very close to 0. Well, this model, this approximation tells us that R infinity is actually 0. Well, it is not in the real life, but it is very small. At the same time, when we cross this point and we're in this interval where beta greater than gamma, we got at any moment of time, we got a finite size of infection. So going back to our pictures, what it really says is when we're in the phase when beta greater than gamma and time goes to infinity, there will be a pretty big R infinity, right? It's this one. Versus if we're in this situation, this is R infinity. It's, well, the simple model predicts that it is equal to 0. It's not equal to 0, but it is small. And the boundaries, the sort of the transition behavior, the behavior changes when beta becomes equal to gamma. So it is exactly as the phase transition in random graph model. Now we're going to see this equation one more time today in a little bit different context. But any questions so far? So this part of the lecture is really not about networks, it's about differential equations, right? It's sort of ordinary differential equations. And I mean, a lot of courses actually like this SI and SIR, SIS models as examples for differential equations because they're sort of clean and have very good applications. Now, one important point here is the following. So as we discussed, R infinity is the total size of the outbreak, right? It's pretty much how many people at the end, recovered or got removed from the system. And this capital R that we introduced, this capital R naught that we introduced, is called is called basic reproduction number. And there is what's called epidemic threshold, where which is R0 equal to 1. This is epidemic threshold. And when R0 is greater than 1, then we have an epidemics. And when it's not, well, we have a recovery, right? No. Now, there exists a very important interpretation of this basic reproduction number. And I mean, the reason it's called basic reproduction number is the following. It's actually equal to an average number of people infected by the person before his recovery, before his or her recovery. Now, let's just think about it. If, on average, every person infects only one person before recovers himself, then it is very clear that you're not going to get epidemics. The total number of infected people as a function of time will pretty much on average stay constant, right? If we had one infected person, well, we'll have one infected person. If a person on average during the period of illness will say infect 2 people, and on average, every other person, every infected person infect 2 more people, and et cetera, that's when you get epidemics, right? You got this sort of exponential growing tree. And if a person infects on average, say this is infected 1 person, but this didn't infect anybody, so on average, the infection rate per person is less than 1, then that's it, epidemics. So the reproduction number tells us is how many people are infected on average by person before his or her recovery. Now, and this is not only this is not only just sort of idea of reproduction number. It's in fact based on our equation. It is what it is. It is what it is. So let's calculate this. So average number of infected people by a person before he recovers. Well, how can you calculate this? Well, we know that on average, we know that a person meets beta people, beta contacts, to infect them, right? On average, so I'm sorry, not on average. The rate of contacts is beta, right? Those that are disease transmitting. Now, if the person is sick during the time tau, during that interval, he will meet beta times tau people, right? Yeah. So every sick person will meet beta times tau people during the period of illness. Now, R naught is an average number of people infected, so it's just an average of this thing. Beta is a constant, right? It's infection rate. What's different for every sick person is the time, how long it's going to be sick. One can easily show that this time is distributed exponentially. So in fact, the distribution of it is given by gamma E minus gamma T, minus gamma T. That is how long a person will be sick. Now, this is probably not the best model in the sense that, in the sense of the reality. This model is usually used to calculate, I don't know, how long time it takes for a bus to come to the stop, right? This sort of exponential time. But that's sort of what the model is giving to us. And if we take this distribution and calculate the average, it will actually be equal to beta over gamma. So indeed, R0, or basic reproductive number, has a meaning of a number of people infected by the person before his recovery. And yes, it is equal to beta over gamma. All right? So that's pretty much it about this SIS, SIR models. The key to remember is in these models, everything is really controlled by the ratio of two parameters, right? The parameter beta and parameter gamma. If the rate of disease is higher than the recovery rate, we get epidemics. If not, we do not, the disease just dies out. And epidemics means that majority of a population will get infected. Okay? So, any questions about this? Okay, so we'll move on. We're going to consider the same problem, the same sort of infection problem. We'll just look at it from a little bit different perspective. In fact, we'll sort of expand our the idea we talked on the previous slides when we looked at the person and how person infects several people, right? We will look at this sort of cascade of infections, and we'll look at this as a random process. It's actually just a model of disease transmission. So now we'll sort of step away from this idea of two compartments, and we'll look at the dynamics where a person can infect other people, right? And those people can infect other people. If you think about this for a sec, yes, this is pretty much how rumors propagate, right? Somebody can tell rumors to two people, and those people can tell rumors to two more people, et cetera, et cetera, et cetera. And so the question is, well, how far will this propagate? So here's the model. The model will be very, very simple. We'll consider the sort of waves of infection, and the waves being how far from the center, how far from the source of infection, the source of the rumor we're at the moment of time. So the first wave of infection will be the first person enters and transmits to each person. But here's the difference. He transmits infection to each person with a probability P. So now we introduce probabilities. So the idea is the following, that when you contact somebody who actually has a disease, it's not necessarily that you get the disease. There is some probability that you catch it. Now, this probability sort of hides inside itself, all kind of mechanics of disease transmission. You can also think about it in terms of, like, say, rumors, that when you meet somebody, well, they can actually tell you or not tell you, right? And it's a random, in some sense, event. And let's assume that we're sort of working in either SIS or SIR model, where the person is contagious for some time. So he's contagious for some time, then recovers. And suppose that he meets K people while he's contagious. So the person has made K contacts while he's contagious, but there is a probability for every contact to actually transmit the disease. And so in some sense, maybe it's just only, say, one person that got infected out of, say, 4 contacts. So we'll use this sort of the tree structure for the contacts, but we'll also use the sort of active links, those links that being used to transmit the disease, and there is just only some of them. And I mean, if there are car people or car total neighbors, and the probability of transmission is P, then on average, of course, it's going to be K times P, number of infected people on average by every person. So then we're going to use the sort of the dynamic model where, okay, well, then the next person, this is the first wave, then there will be the second wave, which is these people start meeting people, and so on. And when they meet people, they either transmit disease or not. And there will be waves, right? So you start with the first person, the first wave, second wave, third wave, etc. Now, the mathematics that we're going to discuss is also, well, very ancient. It was actually used by Galton-Watson, that's sort of the idea of branching stochastic process. And this is sort of the modern notation, modern name for what we're going to do. It's branching stochastic process. So it was proposed by Francis Galton, 1889, as a model for extinction of the family names. So the idea was what he was studying, in fact, was the sort of the pedigree, the structure of the families, and how some noble names disappear. Well, the reason for that is because traditionally the last name is being passed from father to son, right, or father to daughter, but they pass through the male lineage. And if somebody didn't have sons but only daughters, then the passage of the last name will stop. And so some last names will just disappear because of that. And so he built the model that actually predicts how last names, well, and of course he was concerned about names of royalties, how they disappear, right? In fact, there's the same model, it's the same process as we're going to discuss right now. It is very similar process, that's in fact controls a lot of things. But the first time it came up was him. So this is pretty much what I was talking about on the previous slide. The idea is the following. Every person, let's say, in this picture, we have this the tree, and every person meets 3 people. And here is our first wave. So first wave, second wave, etc. And every time somebody meets, there is a probability that infection will be transmitted. And the same on the next level, and the same on the next level. And so what could happen is the following. We could have 2 different scenarios. One scenario is, okay, well, this person got infected, this person got infected, and this person got infected. This one did not, right? Now, in turn, when these people meet with K new people, this person got infected, this person got infected, this person got infected. And in turn, on the next wave, when they meet with more people, well, they infected 2 more people, this infected 2 more, this didn't propagate. And so in this case, we realized that with time, the number of infected people growing. Another scenario is possible when, yes, there is this contact, right? So on the first wave, this guy got infected, but this guy did not. This guy did not transmit infection, and this infected only 1 person. And if the probability of infection is small, well, it just stopped there. And so we got epidemics here, and we got full recovery here. We got rumors spreading and propagating in the first case, and the rumors stopped here on the second sort of level from the person who started them. And so the question is, in this simple model, well, can we calculate the parameter that will control this? So what do you think the parameter would be? So which parameter would differentiate, this versus that?
P times K.
Yeah, it's gonna be P times K. Well, Why?
Because that's the mean number of infected people.
Exactly. Yep, exactly right. So if on average somebody passes the infection only to one person, well, you will get sort of, probably one line going through on average. And if p times k less than 1, it most likely will stop. And if p times k is greater than 1, it's most likely will sort of explode, as on this picture. So what we're going to do in the next 15 minutes, we'll actually confirm this guess with some computations. And these computations, well, they're quite useful because we'll sort of refer to them in the future and some other things. So this is a random process, right? It's random because every time, well, there's a probability that the infection will be transferred or not. And so when we talk about random process, well, we have random variables. So let's define CIN is the number of transmitted infections by each node on the level n. So what it says is, so we have this tree, and we have some level n, the sort of the wave, as we called it before. And every node here can infect nodes on the next level. And so this variable just tells us for the node I, say this is a node I, on the level n, how many other nodes it actually infects. It's a random variable. It can be, one node, 0 nodes, or maximum up to k nodes. Then the total number, if we define z sub n as a total number of infected people at every level, then we can actually calculate the following, right? The total number of infected people on the level n plus 1, here there's the blue nodes, is just the total sum of these random variables, and the random variables cn, they are referred to this eth level, and there are zn of them. Now, z0 is actually equal to 1, because that's where the whole thing starts. Now, it's a random variable. Anytime we deal with random variables, you might want to look at some averages, and that's usually the sort of the easiest way to handle those things. So average number of infected people, right? So average of this C and I, we already talked about it. It's just P times K, because every person has K contact, and P is the probability that they're going to be infected. So P times K, or this R naught, is an average of this random variable. Right? So again, every node can infect either 0 people, 1, 2, etc., up to K. But infection happens with a probability P, so the average will be P times K. What we can do is, by looking at the averages, we can actually write a recursion and solve it. So average number of infected people on this level, and now we're talking about averages, right? Well, I'll just substitute this equation. I'll just substitute this value from here. And because it's average of the sum of random variables, well, we will have to do average of every variable. And since this is also a random variable, we'll not just multiply by it, but we'll multiply by average of that, mathematical expectation. Well, E of Zn stays there, and average of Cin, it's just P times K. And so we got a recursion that really says that E Zn plus 1 is equal P times K, E on the nth level. And we know that average on the zeros level is equal to 1. So just, this, we can unroll this recursion by substituting, right? Because this E zn plus 1, pk times E times zn, well, E from zn can be written as pk average of zn minus 1, etc., etc. And if we do that, you can easily see that E as a function of zn is p times k to the power n. I mean, it's not a big surprise, right? On every level, there is a p times k number of contacts infected. Well, there are n levels. That's what you get. Now, this happens, of course, only because the contact structure we're considering is a tree. Next lecture, we'll talk about actual graphs, where the structure is not tree-like, and you'll not be able to write down this recursion easily. Now, recursion happens just because it's a tree. So what we got is the following. It's pretty much the confirmation of the ideas we developed in the first part of the lecture. So if R naught is equal to 1, so the mean number of infected nodes does not change, right? And that means that on average, well, we'll have this sort of 1 propagation. If R naught is greater than 1, so pk greater than 1, which means we'll get more and more infections. And as time goes by, we get lots of infections. And if R naught is less than 1, then after a few steps, the infection vanishes, right? And it's kind of obvious also by looking at this values, right? If R naught is greater than 1, well, you multiply R naught times R naught times R naught, and it's greater than 1, what's geometric growth, right? If it's less, it eventually will get to 0. So the average number of infected people will go to 0. All right, so this is good. But what we really would like to do is to be able to calculate the probabilities. So the question is, so what's the probability that, say, Zn, when we go to pretty far and goes to infinity, sort of what's the probability, for example, that Zn is equal to 0? Remember, Zn is the number of infected people on the nth level. Or what's the probability that Dn is not equal to 0 when n goes to infinity? So we want to figure out the probability that we're going to get a cascade, we're going to get people infected, and things going to multiply, become an epidemics or not. And to do this, we again sort of do recursion. We'll just do recursion on the probability. Sort of, again, this is sort of the standard trick how you calculate this type of things. Let Qn be the probability that infection exists after n steps. So we have multiple levels of this tree, and we're saying that, okay, let's Qn be the probability that infection survived to this level of the tree, right? So we're going to write right now in a recursion for this. Let's think about this process. So for infection to survive to this nth level, it should propagate to the first connection and then survive n-1 level. So there are different ways to get onto this nth level. So you can go through this connection and survive here. You can go through this connection and survive here. You can go through this connection. Well, infection can go through this connection and survive here. Or it can go through this connection, and in both cases survives. This all situation gives us the survival of infection. So in this sense, it's easier to calculate not the survival of infection, but the fact that infection will not survive through this, right? Because for infection to survive, there are multiple ways, and then you need to really, because these are independent paths, you will have to add the probabilities, right? But if you're dealing with not survival, right? Not survival, then it's easier. Why is it easier? Well, let's look at this. So if Qn is the probability that infection survives n steps, Qn minus 1 is the probability that survives n minus 1 steps, let's say here. Then it's the probability that infection actually survives this branch of a tree is P, which means the probability to go on one link, times Qn minus 1. So it spreads to the first contact, one of the first contacts, and then survives n minus 1 level. Now, the probability that infection does not spread through this path is 1 minus P, Q, and minus 1. This is a probability that infection does not go through this path. The probability that infection does not go through any of these paths is 1 minus PQN to the power k. So this is the trick. Instead of looking at the at the probability that infection will go, we'll look at the complementary. We'll look at the complementary event that it doesn't go. And if it doesn't go through neither of the paths. And that means, since these are independent paths, we can just multiply the probability that it doesn't go through each of them. Right? So the probability that it doesn't go through any of those paths is 1 minus P, Q, and minus K. Well, this is it. But that means it is equal to the probability that infection starting at the root never gets to the bottom. And that means 1 minus Qn, because Qn is the probability that it gets there. All right, so again, we switched to this logic of complementary events simply because if we were calculating events themselves, we would have to take into account all the possible combination of passes. And if we're looking at complementary events and we're saying that it never get there, well, if it never gets there, it shouldn't get through this, shouldn't get through this, it shouldn't get through this. And this all events independent and should happen. And all of them should happen. And so that means we multiply through their probabilities. And that gives us this recursive equation. Think about this. It's a kind of useful trick to actually go from events to the complementaries. Well, if we look at this recurrence, here it is again. The only thing I've done here is I just moved it on a different side. We can actually go through this recurrence and calculate it. U naught is equal to 1. We start with one infected node. And again, Qn is a probability that infection persists through n steps. So remember, we have these two parameters, the parameter P, which is a probability that neighbors get infected, and parameter K, that it is the number of neighbors. So there are two possibilities here. Depending on these parameters, P and K, we can, for example, we start here. Okay, what's shown here, this is obviously y equal to x. This is diagonal, and this is the value of this function. So what we can do is we start at some point, value of this function. We substitute in, so we start at 1. We calculate the value of this function. It is here. What we need to do after that is, take this value and, plug it back here. You can geometrically do it by projecting onto the diagonal and going down. And so this will be the next step, the next value of this recursive iterations. And then will be the next value, and the next, and the next, and the next, and the next. And eventually, we'll get that when n goes to infinity is equal to 0. And so the recurrence, it's a probability that infection persists through n steps. So this really means that infection dies out. All right, the probability that infection persists through n steps is equal to 0. Well, there is another possibility, depends on P and Q. These curves can be aligned differently. And then after several iterations, we get here, and the fixed point of the iterations, and it's called fixed point of iterations, is right there. And it's different from 0, so Qn is not equal to 0. So there is non-zero probability that infection persists after n steps when n goes to infinity. And so that means epidemics. All right, so it's sort of, we keep confirming the same idea, that it is this, the ratio of beta to gamma, or something about P and K that tells us if there is epidemics or not. But remember, on the previous slides, we actually said, okay, P times K, this is the number that we're concerned about. In this sequence, I don't see P times K. What's up with that? P is down here, K is up there. There is no product P times K. It's clear that there is P and K, but there is no product. And we're always talking about that it's a product of P times K that is important. What am I missing? Yeah, exactly. If you look at this and think about this exponent, what you're going to have here is e minus p q n minus 1 to the power k, which is, of course, will be e to the minus pk, right? So it is, again, will be p times k. And of course, we can look and do the same thing as we did before. We can try to figure out what happens, when can we actually find the non-zero solution of this equation. It's exactly the same story as we previously did, which means we need to look at this curve, which is this one, versus a straight line, and see, look at the slopes at origin. And again, if we calculate slopes at origin, we'll get this equation, pk equal to 1. So bottom line is, whatever we do in these models, whether we look at this SIS models, SIR models, where we look at the branching process, there is always this number, which is in terms of this basic reproductive number that tells us that during their infection time, how many people particular person can infect. And this number can be calculated as beta over gamma if we look at the differential equation approach, or can be calculated as a probability of infection times the number of neighbors it can infect. This number controls the infection, and if it is greater than 1, we get epidemics. And if it's less than 1, we do not have epidemics. It is a phase transition, and it is, very, very closely related to the phase transition we observed in random graphs. So that's it for today. Any questions? Okay, as always, there's no question. I don't know if it's absolutely clear or absolutely not clear. Or we'll learn during the project and the finals. Okay, so we'll learn during the finals. All right. Okay, fine. Fair game. So there are some references for this. There were sort of original paper. Well, I couldn't find the original paper from 1881, though I'm sure it exists from Galton. But there were the papers from Kermack McKendrick. They're available. And there was a pretty good review, if you're interested in this topic. There's a pretty good, contemporary review from Siam on mathematics on infectious disease. And there are some chapters on this topic also in the book by Newman on the book on networks. So that's pretty much it for today. Okay, we're done.